Good day, everybody. Again, this is Tim, Tech Talks with Tim at Duraloy Technologies. Once again, joining me, I've got Mr. Raymond Monroe, the Executive Vice President of the Steel Founders Society of America. Ray, again, welcome to the program.
Thank you. Thank you. Good to be here again.
Look, today we're going to talk to you in a minute about forging, welding, machining, and casting. Ray's going to give us a little presentation on that. But Ray, before that, I just want to give you a thanks for what you guys do. You guys are coming off this big Thor competition, where you get all the colleges together. You care to share a little bit about that? Because from my perspective, we appreciate what you guys do for the next generation of steel makers.
Yeah, let me pull that up because I think it'll be really fun for people to look at. So let me put my share screen. I assume you can see that now.
Yes, sir. It's up.
Yeah, and this is just my title slide. We're going to talk about forging, welding, machining, and casting, to talk about the different ways we make steel parts. But we actually are trying to get the next generation of engineers excited about steel, both for our customers, our suppliers, and certainly in our industry. And so we've been sponsoring, this is our third year of sponsoring a cast and steel competition. And the idea behind the cast and steel competition is to use a forged in fire kind of event to get colleges to have teams of students that make something as a casting. There's this sort of implicit thing that comes from 2,000 years of having to forge things to make it into steel, that somehow if you don't hit a piece of steel with a hammer, it's not strong enough. And that's just incorrect. Yeah. So we want to let the students experience the technology of making castings. And of course, it's a high-tech industry. So the universities are just blown away when they get to see what we do, because we actually have solidification modeling, solid modeling, FEA analysis, all of that goes into it. And so this year we challenged the students to make a Thor's hammer, and we've just been blown away with the success. So we had 27 Thor's hammers made, even during the pandemic. And we match up the students with a industry partner like Duraloy and a university project. And one of the biggest benefits we got, the very first year, I thought we might get 5 people to make a Viking axe, and we had 20 Viking axes made. And so I reached out as an old association guy to the celebrities in Forged in Fire. And if you look on this slide, this is Ben Abbott, who's the 2-time champion and judge from Forged in Fire. And he's become a real partner in doing the competition. So he's been just terrific to work with. And of course, the kids get thrilled because he may be a little celebrity in the world of Hollywood, but among college students who are making Bowie knives or Viking axes in the competition, he's a hero. And so next year, we're certainly planning to have Ben at the competition and do it in April and let the students actually do the competition. But this year we did the Thor's hammer, and it's just been a delight. So thanks for letting me plug that. I think it's just terrific. If you go to Cast and Steel, our website, you can actually watch the videos, and the videos are just really terrific. They're just a lot of fun. If you're interested in the local university, the local university will, if they competed in the Thor's competition, they'll have their own video of the manufacture of their hammer, their technical report, and their competition. You'll get to see Ben Abbott smash stuff with their hammer. So that was a lot of fun. So thanks for that. It's really just a terrific event. The students get a big kick. The universities learn about our industry. The industry gets students interested in steel, which is not really that popular in the university community anymore. So that's a lot of fun.
And Duraloy is located in Pennsylvania. Who happened to win the competition?
Yeah, we actually, the best technical report was Penn State Barron's. Paul Lynch up at Barron's had the best technical report. And so he did a really nice job up there. We keep trying to get Bob Voigt up at Penn State to have a team. and then a John DuPont down at Lehigh. But we're really excited. We had some of the big name schools this year participate as well. Texas A&M University, Colorado School of Mines, and they just had a great time doing it. A lot of the universities are using it as a senior project.
That was just my shameless plug for Pennsylvania Steel. I'm just
yes, yeah.
All right.
Well,
Thanks,
yeah,
Ray.
that's a great thing. All right,
Let's get on with the with what we're really here to talk about.
yeah.
Welding.
One of the things people should realize is that all steel is cast. We may do other things to it after we cast it, but steel doesn't start out with some other manufacturing process. We don't make steel by mixing it up in a mixer. We make steel by melting it. And most of the steel, that is the majority of steel made in the United States, is melted from scrap in an electric arc furnace, and we use electric arc furnaces and induction furnaces. So foundries make steel just the way everybody else makes steel. The steel we make really used to be the critical part of the process. So the name steel foundry is an old terminology when anybody that could melt steel would make every kind of steel product. Just like in the old days, a carpenter would make anything. He started with trees and ended up with furniture.
Right.
In the early days of the steel industry, anybody who could melt steel could roll it out to make bars and plates, could forge it, or could cast it. And most of the steel mills had their own foundry to make large castings. So casting has always been a part of the steel industry during the modern industrial age. We're going to talk about the different kinds of products that are made. So because you and I had talked earlier about the fact that people will say, we got a steel plant in our neighborhood, you probably know those guys. And you go, yeah, there's 200,000 people in the steel industry. No, I probably don't know those guys. Right. And they probably make something different than I make. But it'd be useful for people to have some intuitions about what kinds of products the different processes make. And so we're going to talk about the traditional processes. And in the traditional processes, you mainly used shapes that were easy to roll. So you use standard shapes that could be made really inexpensively, whether it was a tube or a plate or a bar. And then you either cut them out like cookies and welded them together, or you took a big chunk of steel and machined away everything you didn't want, or you actually did both. You made parts like this and then welded them together so that you got the component you wanted. And the steel using these traditional methods is relatively inexpensive, but making the shape is where all the funding is. And so that's really what happens there. And so that's where additive manufacturing today and historically casting really added value, because this is not a cheap way to make steel, but it can be the most efficient and highest performance way to make actual components. Forging is a way of improving the properties of steel, and you can make simple shapes with forging. So we're going to go through these processes to give you a sense of how they operate. Now, in the modern steel industry, this is how we operate. And so traditionally, we took coal and iron ore, and we turned the coal into charcoal made with coal. So charcoal made with coal is what coke is. You take the coal and you partially burn it to get rid of all the water and the crap in it. And then you use the coke with the iron ore and limestone in a big tall furnace like those old stone furnaces, but these are huge furnaces, and you turn it into cast iron. You can take that cast iron and make pig iron, and then you can use that to make ductile iron or gray iron. That's not steel. That's not very weldable. That doesn't have the high properties, but that's a really good casting material if you're making engine blocks and other things.
Right.
Most of that blast furnace iron would go into a basic oxygen furnace. Here you use carbon to take the oxygen away from the iron ore. Here you use oxygen to take the extra carbon out to make it into steel. And then you can go into the casting operation, which could be continuous casting or ingot making. With Nucor, this is what U.S. Steel did. This is U.S. Steel. Up here, the arc furnace, Ken Iverson and the people at Nucor realized I could put in an arc furnace and melt scrap and make steel inexpensively and use continuous casting to make the product. So this is the modern mini mill industry. So this is the integrated steel industry. This is the mini mill industry. The electric arc furnace guys didn't want to depend on buying all of their pig iron and that from the blast furnace. So they've been inventing using natural gas to get the oxygen out of the ore with direct reduction. But most of the steel made in the arc furnace is used as scrap. And because you have so much carbon here, about 30% of the blast furnace iron that turns into steel is scrap. So in the US, we make about 90 million tons of steel a year, and we use up about 70 million tons of scrap. So that
the biggest green organizations in the world are your steel mills.
Absolutely. In fact, the piece of steel you touch probably has atoms that were in some Roman sword. That's how recyclable it is. We recycle everything.
Yes.
And so all the steel is cast. It may be cast continuously or in an ingot or as a casting. So this is how ingots work. And this was the traditional way of making steel, where you would pour ingots in a metal mold, and then you would use those ingots to roll into bars and plates or to turn into forgings. So these ingots would get completely cold. You'd have to reheat them. Then you would have to break down a great big ingot into a small ingot. So continuous casting meant that you didn't have to do all that work. And continuous casting was really cool. You take the liquid steel, you pour it into a tundish, which is really just a big refractory bathtub with a hole in the bottom. You open the drain, which is the nozzle. The steel goes into a copper mold. This copper mold allows the steel to solidify on the outside while it's still liquid on the inside. And then you continue to pull that out while it solidifies, so that at the top, you're pouring liquid steel in, and at the bottom, you're pulling out a solid bar. It's a really cool process. And these are huge plants. Their arc furnaces are 300 ton furnaces, 100-ton furnaces. And they can make anything from these plates to bars to rail to wide flange shapes, I-beams and C-beams. And so this is the way most of the steel is made. And this is a really inexpensive way to make bulk steel. Most of the steel that foundries work with, like you at Duraloy, Tim, make, are really specialty steels. And out of that 90 million tons, only about 10 million tons is specialty stuff. So traditionally, what we did was we welded together pieces that we'd made either by machining or cutting them out of regular shapes. And the idea behind that was the steel was as cheap as you could buy steel. The challenge is you spend all your money making the shape you want, making the components you want. So you can get fast assembly times, you can set it up and automate it, you can customize it, but it's an expensive way to do it. It may be the cheapest way to get there today,
right?
But the cheap stuff is normally when you can cut it out of cookies and weld it together. So that's how we fabricate buildings. Making things with machining, even when you machine a casting, frequently the machining of the casting costs twice as much as buying the casting geometry, because machining is really the high cost manufacturing production method. So in forging, what you do is you take that ingot that you made and you bring it over to a forge and you squish it down. Now, the challenge is people think squishing it down moves the atoms closer together, and that's not correct. You don't get better properties because you squish the atoms together. The reason you get better properties is because this is just a big bread mixer, and it mixes the steel up so you get uniform properties everywhere.
Right.
And so one of their main products is taking big ingots and making large blocks of steel for people to machine. So most of the large block stuff is really supplying raw material that's got better properties. And when they forge it, they get better properties in the direction they smush it, but poorer properties across it, because any of the little pieces of dirt in there that used to be little round balls and had the same properties everywhere, they turn them into pancakes. And so when you look down the edge of the pancake, you get really good properties. But when you look across the pancake, right, the properties aren't so good.
Yeah.
So that's a really interesting thing. So you can really get good properties, and that's how you make large blocks to make dies
Right.
for automotive presses or for die casting or for forging operations. You can also make really high volume, really simple parts. So if you're going to make a hammerhead, which is about as simple a part as you can make, forging it is a really cheap way to make a hammerhead. And so when you go to the hardware store, you'll see drop forged wrenches and
Yep.
drop forged hammers. And
Yep.
that's because you can really make inexpensive, high performing parts with by having a small die that lets you make that. Originally, everybody thought that that gave you great properties, and so they were dismissive of castings. But Ruger, the handgun company, made their money by lowering the cost of making firearms by using investment castings. And originally, when they came out, all the other handgun manufacturers said that's poor quality and you won't get good performance. But Ruger showed that it's just as good as any forging. And so they really got a great market by using the investment casting process. And investment casting is used by everybody, including the military, to make small arms now. The real challenge with forging is because you're hitting it with a hammer from both sides, you have a real limit on how complicated the part can be.
Right.
Generally, you just make a rough form and then you have to do machining to get the final part. And then also, what alloys you can get are really limited. If it's a common alloy, you can buy a bar or plate and use it to forge, especially for these low cost volume parts. If you want a large block, you can buy a heat of steel from the forge shop, but that's going to be expensive because that's a small lot. So that's really the forging stuff. Then, of course, additive manufacturing is the new thing. In additive, probably the one that's easy to understand is just to use welding to make the whole part. Use a robot, program it. But all of these additive manufacturings actually are printing techniques where I just make it one layer at a time, like
Right.
printing a big manuscript. So this is a big manuscript I'm printing with a welder. Laser powder bed fusion is the one most people are most excited about because I can make small parts with really tight dimensional tolerances. And I can make parts, but many times after I've designed the part, I can make that complex geometry as a casting. And so these become investment castings or other castings. But additive really is the new thing because that lets me get the geometric complexity with high performance parts. But that's traditionally what the casting industry did. The casting industry can make that complex geometry because we take liquid metal that doesn't care what shape it's in and we pour it into sand molds. And those sand molds allow us to make really complex shapes. And so, and since we make small batches of steel, we can make any alloy that you want. So we can make complex shapes with complex internal holes, valves, pumps, tubes, the kinds of things you make. And then we also, so we can use a permanent pattern that lets us make multiple times that really complex shape. And we use that pattern to make a mold with sand that we glue together with some organic binder, or we used to use clay and water like we were making pottery. That's green sand.
Yep.
Once we have that mold, then we can pour liquid metal and it takes the shape we want, but we have to have a plumbing system. And so we have to cut the plumbing system off to get the part we want. So this is really the casting value is that you can have any alloy you want, you can have any complex geometry, but we have to be smart in the way that we do the engineering. And so one of the ways we do that is we use casting simulation modeling, which lets us model how we fill the casting to make sure that we get a nice quiescent flow and don't catch crap in it. And then we also can watch it solidify. And we use solidification modeling to try and make sure that we get the part completely solid. We really have been some of the early users of additive manufacturing. We were the first adopters as foundries. So one of the things we do now is we print the sand cores and molds that allow us to make really complex shapes without having first to buy a mold, a pattern, or a die. And this allows our modern customers to try 4 different designs at the same time without having to buy tooling first. And it allows us to make really complex shapes that would require 5 and 6 cores and would be difficult to make dimensionally accurate. We can make them accurate. So we also are using additive robotic arc welding. We can use it to add features. We can use it when we find something that is out of spec and we remove material to replace the material. And so this has really been a benefit using additive in our production processes. So this is sort of a summary of all of that. You can stop the video, I guess, at some point and look at all of this, or Tim can provide it for you. But this really just covers what you saw, what's the value of each one of these process and what's the limitation. And so I don't want us to go on too long, Tim. So this is really, I think, the summary of it. And it was just to give everybody a taste of how these different manufacturing processes work, what's their sweet spot for manufacturing, and what are their limits.
Yeah, and thanks, Ray. This is kind of what we had talked about, was getting ourselves to this point where we just give an overview of steel manufacturing, and like you and I talked about before, is people drive down the road and they go, yeah, they make steel in there, but you know, what kind of steel do they make? It's not all the same. And so again, we'll have you back sometime in the not too distant future. We'll talk about more different ways you guys help the steel industry, but also just the value of steel and what it does for all these industries, how it's used. Again, I can't thank you enough. We appreciate what you guys do for us at the Steel Founders Society. If you're watching the video, please like it, share it, comment. If there's a topic you'd like me to talk to Ray or anyone else about, please send us a message. Again, Ray, thank you. Appreciate it.
Thank you. This is fun. It's fun talking with you, Tim. I always enjoy doing this, and it's always fun to talk about steel. So thanks.